All right, we're back. So now we're going to talk about the periodic table. So early periodic tables used different symbols and sometimes included compounds and not just elements. One of those was made by Dalton, which you see here, this periodic table of elements that he designed. We got some similar ones that we've heard of before: hydrogen, carbon, oxygen, phosphorus, sulfur. But then we've got some down here that are not actually elements. Magnesia, lime, soda, potash, those are actually compounds. So potash is a compound made of potassium. Lime is a compound made of calcium, I think, or soda. I'm not sure which. I never remember which is which, but one of them is made of calcium, but it's not an element, it's a compound. So they didn't really even know what elements were. They were just kind of guessing and going off of what they could observe in nature. The first modern periodic table was designed by Dmitry Mendeleev in 1869. So it didn't look quite like the periodic table we have now, but it was a lot closer than this. And just a fun fact, last year was the periodic table's 150th birthday. So happy birthday. All right, so the awesome thing about Mendeleev's periodic table was that he accurately predicted the properties of several elements before they were even discovered. For example, he called this element Ea, where we know this element now as gallium, but he predicted all of these properties before they ever even discovered this element. So he predicted its atomic weight. He was pretty close. He predicted its density. He was pretty close. He predicted the valence. So you don't know what valence is yet, maybe. You remember from high school, but we're going to get there. Don't worry about it. But he predicted it. Isn't that cool? And he also predicted properties of the oxide, so the compound made between gallium and oxygen. That's so incredible that he predicted these properties of an element that didn't even exist. And he did that because of the structure and the foolproof structure of the periodic table that he designed. So this is our more modern periodic table, but what do I mean by the structure of the periodic table? I mean that gallium, for example, is right here. Gallium is in group 3A or group 13. So the traditional way to call these groups, which are the columns of the periodic table, they're groups. The traditional way to call them is by this number with an A, but the standard now in chemistry is the number just 13, 14, 15. So 1, 2, and then we number the ones down here in this block, and then we come back up to 13. So 13 goes with 3A, 14 goes with 4A, so it's not too hard for people to figure out if they are used to the original numbering system like I am. But you guys just need to worry about the 1, 2, 1 through 18, those group numbers. So all of the elements in a group have similar properties. So that's how he was able to predict the properties of gallium, because he knew the properties of aluminum and he figured they would be similar, and they were. So because he organized his periodic table based on properties of the ones that he had in his possession so far, so they hadn't yet discovered gallium, but they had carbon. These were all on the really old periodic table even. They had carbon, nitrogen, oxygen, phosphorus, sulfur. They knew all of these existed so far. So, and I guess aluminum. So because they knew these ones existed, they could compare their properties, and he found that oxygen and sulfur had pretty similar properties. Nitrogen and phosphorus, carbon and silicon, boron and aluminum. They have similar properties, so he grouped them together in a way that all of the elements in this group going straight down the column have similar properties. So he was able to predict properties of ones that were not discovered yet, and it's awesome. It also helps that everybody uses the same periodic table now. It's standardized, just like our units that we discussed before, the SI units, units of mass, length, time, whatever. They're standardized, and so is our periodic table. So the columns are called groups, or sometimes called families, whereas the rows, when we go across a row, these are called periods. So if you wanted to find, for example, a element that is in group 2, period 6, you'd look for the group first. This is group 2, and this is period 6. So you must be talking about barium. It's the only one that's in group 2 in period 6. So that's one way that we can make sure we're talking about the same elements, which is really useful when you're working with people from completely other countries, different age groups, everything. Really helpful to have common terminology. What else can we get from this periodic table? So it tells us what kinds of elements these are. So all of the elements over here in this light blue are called main group metals. All of these dark blue ones, oh, sorry, there are some light blue ones over here too, huh? All the dark blue ones are called transition metals. They transition from the main group metals to the non-metals. The green ones here, there's not very many that end up being in the green. They are metalloids. So they have some properties of metals and some properties of non-metals. And then all of the orange, including hydrogen, which can never decide if it's going to be in group 1 or over here in group 17. Hydrogen has some properties in common with group 1 and some properties common with group 17. So you can find it in either place sometimes on the periodic table. And one of those properties that it has in common with group 17 is that it is a non-metal, like the other orange elements here. So that's really useful to know about metals and non-metals. For example, all these metals, pretty much all, there are some weird exceptions, come as solids. They're usually shiny and can be, what's the word? Pretty durable. But whereas our non-metals in the orange over here, they're not usually solids. Some of them are, but most of them are gases, actually, over here. So, and if they are solids, they are not shiny and they're pretty brittle. So those are the differences between metals and non-metals. One other difference, or sorry, one unique thing, some unique metals are mercury, for example. Mercury is Hg. Mercury is the only metal that is a liquid in its natural form. So that's one weird thing to remember. Bromine over here is a liquid. Iodine is a solid, but everything else in this like top left corner is a gas. So you should be able to tell certain things from the periodic table. You should memorize certain things about the periodic table, like where the metals are versus the non-metals, what groups or families certain numbers refer to, and how to find an element based on its period and group number, like we did here with barium. All right, Cool. So some groups or families of elements have common names. For example, group 1 are the alkali metals. Group 2 are the alkaline earth metals. Group 16 are called chalcogens. Group 17 are called halogens, and group 18 are the noble gases. So we'll talk more about all of these types of elements, all these families of elements later, but try and remember those five names for the families of elements. And then one more fun fact about the periodic table is that elements come in several forms. Sometimes they come as single atoms, like the noble gases. Sometimes they come as diatomic gases, like I briefly mentioned for hydrogen, oxygen. So those diatomic molecules look like this. Sometimes they come as metallic lattice structures. I mentioned that is also a representation of an element, even though it's got lots of atoms included. And sometimes they can come as these weird 3D networks. We'll see more of these structures in chapter 5. You don't need to remember any of those right now. All right, I'm going to pause here again, and then we'll talk about the mole.